Good afternoon to everyone. Welcome back to this 10th lecture in the Energy Data and Modeling program by the International Energy Agency. Today we have the pleasure to have with us our partners from Politecnico di Milano, one of our partners in the academic world. They come from Italy, and today they will be presenting you some of their insights on how they use modeling in real-world case studies. Before leaving them the floor, just a brief recap. As I said, today this is part of the two lectures we have with partners. We had Imperial College yesterday, and today we will have Politecnico di Milano. Then tomorrow we will have a lecture on SDG 7, and in particular on access to clean cooking and electricity, so SDG 7.1. Then next week, basically, we will finish this first phase of our training program with solid biofuels estimation model. And then Thursday, we will have a quick wrap-up quiz and closing session in which we will be asking you some questions, very basic questions related to the topics we addressed during this program. So I leave the floor to Politecnico di Milano. Just remind you that if you have questions, feel free to write in the chat, in the Q&A box, or to raise your hand so that I can give you the floor. You can unmute yourselves, also turn on your camera and ask directly the questions to our colleagues from Politecnico di Milano. So I think Francesco is the first to talk. The floor is yours. Thank you.
Thank you, Darlene, for the introduction. I'm Francesco Tonini, doctoral researcher at Politecnico di Milano, and I bring you also the greetings from Professor Emanuela Colombo, who is our group leader here at the Department of Energy. My duty for today is to give you a brief insight on which are the main challenges of the energy world, and especially which are the challenges here at Politecnico we are addressing, and with which instruments. Energy, first of all, is internationally known as a driver for sustainable development and a driver to reach all the other goals of the Agenda 2030. Is fundamental for socioeconomic development. It is at the basis of the quality of life of people, but it is also very relevant also for issue related to global security and environmental protection. And this is the reason why during years, energy and the related issue have gained a lot of interest in the international meetings about climate change and the one related to sustainable energy for all. This because we as humankind are at a urgent turning point. We are now realizing that there are no chances for sustainable development to occur without changing the pattern of our consumption and over-exploitation of natural resources. But on the other way around, it is clear that a sudden shortage of energy supply will put under severe threat our economies, and especially developing economies that are the one who need major attention. And the way to solve this challenge can be taken from the definition of the sustainable development itself, in which three are the fundamental dimensions: the economic, the social, and the environmental one. So going step by step to understanding each one of those dimensions, I will start with the environmental one that give us the boundaries in which the development can occur. It is necessary for us as a modeler or for policymaker to take properly into consideration that the resources in the universe are limited. And so our growth is bounded by the physical constraints that are around the environment. Therefore, a growth pattern like the one experienced in the past is no longer acceptable. And and also, if we look to the other two dimensions, we see that the issue between the issue related to energy and resource consumption is crucial, because if we look to the correlation between the available energy for people that is measured accordingly to the total energy supply per capita, and we see its relation with the gross national income per capita, which is a proxy of income per capita, we see that there is a strong relation, especially in those countries that are at the first stage of development. With the bubbles you see in the graph, countries at a different stage of the development. With light blue, there is medium human development countries, with the yellow high human development countries, and with the red, the very high human development countries. So we see that for medium human development country especially, there is a strong correlation. And this means that an additional unit of energy is crucial to have a potential growth in terms of available income. Then when we reach the very high development countries, we see that this correlation is becoming weaker, because in such cases, there are other dynamics that become relevant for development. For example, you can consider US and Europe that are more or less at the same level of development, but the two regions are experiencing a very huge difference for what concerns the total energy supply per capita. And this relation is even more evident if we look to another indicator. This indicator, the Human Development Index, is putting together with the economy also the dimension related to education and health, providing aggregate information about, generally speaking, the level of welfare of a nation. And you see that the relation with energy of this indicator is even steeper at the low stage of development. It means that the use of energy is even more crucial if we look to our social development in general. And the relation is flattened, coming to high level of development. And this is what we are expecting even by looking to the first graph. So this gives me the chance to highlight another very important issue, that is the fact that energy is very linked to justice. I'm not a philosopher, I'm an engineer, but I like to contaminate my research activities with some insights that come from other fields of expertise. And this gave me the chance to reason about the fact that energy per se is not determining the level of human dignity. Nevertheless, energy is a fundamental right in order to reach all the other rights that determine human dignity. And this is what is highlighted also by the UN institution, that starting from the Millennium Development Goals were putting our attention on this issue. But which is the real condition of our world? The real condition of our world is that a huge number of people is still lacking of reliable sources of energy. In particular, 1 billion people in low-income countries have no access to electricity, and more or less 3 billion still rely on traditional biomass. But also the problem is for middle-income countries where 1 billion people have no access to reliable electricity. That means that they maybe have the connection to electricity, but the grid is not providing the power with a constant supply. And these have a huge drawback in terms of loss of productivity and so loss of growth opportunities. But nobody in the world is, let's say, safe from energy concerns. Even in high-income countries, there are 50 to 75 millions of people that are affected to what is defined fuel poverty. With fuel poverty, it is referred to the condition in which you have to spend more than 5% of your income to pay the energy-related bills. And this is the condition in which a huge number of people are, even in Europe. And this means that those people might have connection to electricity, might have also appliances, heaters and whatsoever, but at the end of the month, they cannot afford the bill, with bad consequences, of course, in their quality of life. Those issues that are related to different countries around the world are exactly the issues focused in the definition of the goal number 7, where the aim is, the target is to ensure universal access, okay, energy access, increase the share of renewable energy, and this is, let's say, a target spread all around the world. But then the issue related to improve energy efficiency, enhance international cooperation, and expand the infrastructure to upgrade the technologies, this is to face those cases in which there are issues related either to lack of reliable sources or lack of affordable technologies. And this brings me to recap with you that together with affordability, there are other well-known issues related to electricity that are related to the issue of flexibility of the grid, reliability of the grid, supply of materials to sustain, especially the energy transition, and also the risk related to the fact that goal number 7 is strictly related to goal number 13, and the way in which it will be possible to reduce CO2 emission is linked to the way in which we will be able to foster the energy transition. And we now are facing an even huge shock in terms of energy supply. That is the situation in which we are now after the COVID-19, where the energy demand fall is something never seen before World War II. And we in Europe are now facing also some difficult situation in terms of energy, also because the war against Ukraine and Russia. And but the problem is that to obtain the so-called just energy transition, it means that no one can be left behind. And so it is necessary to consider that the worst effects of the crisis faced worldwide are felt among the most vulnerable communities, where here it is estimated the number of people that are at risk of losing the ability to pay for electricity bills, and these numbers will increase the amount of people that are in a fuel poverty condition. And here I reported also a graph related to access to energy that it is, I think, well known. So now the issue, the point is how it is possible to tackle this complex condition, and which are the instruments that can enable us to provide the decision makers with insightful information for future energy paths. Our approach here at Politecnico di Milano is listed in those 4 bullet points, because our thought is that research have to be at the service of policy making, and the 2 activities have to be strictly linked. And technology and innovation is crucial in this process, and you have to remember that innovation it does not mean necessarily to have a new technology. Innovation is also using current technologies in a new way. And to do this, it is important to see also how citizens are behaving, because the technological innovation has to be at the service of people. And an overarching principle is based on the principle of international cooperation that can boost the efforts toward the energy transition. But what we have to remember is that essentially all the models are wrong, but some are useful. And this gives me the chance to remember that models are instruments that can enable us to find insightful information, but they are not providing any truth, basically. So to give you an overarching perspective on the instrument we have, our approach is based on 3 different layers. At the first one, there is the description of the technology itself with basically some lumped parameter instruments that are the input of the second layer, in which the focus is on the energy system itself, and the link with the third layer is related to the fact that the energy sector has multiple interconnection with all the other sectors in the economies. But I'll go a bit further in detailing what I mean with all these layers. The first one is related to having a precise LCA footprint quantification of different consumption good, or having a precise description of the load profiles for energy technologies, and also trying to forecasting some evolution over time of aggregated parameters related to energy. While in the second layer, we are using different system modeling approaches based on optimization algorithm, basically. The third layer indeed is related to industrial ecologies instruments that you will see further in detail with my colleague Nicolò Golinucci. While indeed the second layer, it will be deepened by my colleague Nicolò Stevanato. So the use of this framework based on the three different layers is aimed at providing a multidimensional perspective about a possible intervention in the field of energy, with also a deeper focus on the sustainable development goals that, as you can see in this figure, can be addressed in a multiple way by using the different layers. So I stop here my brief introduction to leave the floor to my colleagues that, as I told you, will deepen the two main layers of the framework I presented. So thank you very much, but I'm here to answer a question if you have. Okay.
Darlene, I don't see PowerPoint among the possible applications to share. I don't know if it's my problem or something changed in the. I only have the whiteboard among the things I can share.
You should be able to, but you can try to share your screen maybe.
I don't even see the screen among the things I can share. Let me close PowerPoint for a second. Sorry for that.
No worries.
I switched to Francesco computer because I cannot share anymore my screen. Sorry.
Okay, no problem. Okay, now it's
okay.
okay.
Great. Sorry about that. Okay, so my name is Nicola Stevanato. I'm also a PhD candidate at Politecnico di Milano Department of Energy, together with Francesco. And I will briefly introduce you to some examples and some basic theory of energy modeling that we carry out for local development here at the Department of Energy. Okay. So as you know perfectly, the issue of access to energy poses a question in terms of energy planning, because the majority of population without access to electricity resides in rural areas of developing countries, and the grid extension, for this reason, is often not the best option in terms of economic cost and the viability of deployment. And for this reason, other technological options started to come forward as better solutions to provide electricity to communities. The smallest solution is the standalone option, usually in the form of a solar home system. It can serve a single user. Usually it's well below 1 kilowatt of power, and it's suitable for very sparsely populated areas, characterized also by very low energy demand. Some examples are diesel generators, rooftop PV, mini wind turbine, and could or could not include a small battery pack. The second technological option is the MiniGrid technology. There is an isolated energy system that supplies energy to multiple users and can rely on different energy sources, such as, for example, hybrid mini-grids with the PV and diesel generators. Often they have a battery pack to store energy and decouple generation and consumption of energy. Their size is usually below 500 kilowatts, and their main characteristic is that they are able to cover not only residential loads, but also productive uses of electricity. While the third option is, of course, grid expansion. It's more suitable for very high load demand areas characterized by high density population. Energy system modeling can support scientifically, in a data-driven approach, this strategy identification, both in terms of understanding what is the best technological solution to provide access to energy. It is the case of geospatial electrification models, or by providing optimal sizing of the identified technology, and it's the case of energy system models. As Francesco said, in our research group, we have this three-layer approach, and in my presentation, I will talk about layer 1 and layer 2, so characterization of appliances, of components, and energy system characterization, sizing, and optimal dispatch strategy. I will try to give a brief definition of what is energy modeling. It's mathematical representation of a physical phenomena. In our case, the physical phenomena is the energy system, in order to perform experiments by assessing scenarios, adaptations, and derive insights for future policies. So since I cannot make a laboratory experiment about an energy system, I create a mathematical representation on my computer, and I use that to assess the results of my experiment. The models, energy system models, wide extremely, both in temporal resolution and in geographical resolution. It means that I can model from sub-seconds, if I'm dealing with specifically electric models, up to decades, and I can cover from a mini-grid, for example, so you have the regional, the geographical coverage of a single village, up to national models, continental models, or even global models. In this specific intervention, we will focus on supply generation and optimal dispatch models. So the output I'm interested in is the size of the supply and the optimal dispatch of these energy systems. The most basic, or let's say the typical energy system model sees as inputs the load demand, because in the end, the final goal of my modeling is always to satisfy a demand, so guarantee that my population experiences energy security. Then I have, as a second category of inputs, availability of local resources. Since I'm often dealing with renewable sources, I have time variant availability of renewable sources. Techno-economic parameters per technology, meaning that I have to characterize the specific costs of installation and of operation of every piece of technology that I'm considering in my modeling. And planning parameters, that is an easy way to refer to all these parameters, such as discount rate, how many years am I modeling, and stuff like that. As an output, for this category of models, I expect optimal capacity, optimal dispatch strategy as primary results. And then from them, I can derive, for example, the net present cost of my project, the levelized cost of electricity, and a detail of all the investment cost and all the operation and maintenance costs that I will face with my energy system that I'm sizing. The first step when performing energy modeling is the definition of the reference energy system. So if I'm dealing, for example, with a country level energy model, I have to, before starting the modeling phase, have clearly in mind all the technology involved, all the energy fluxes involved, and how technologies and energy fluxes are connected one to the other. This is an example of a generic reference energy system for a country with natural gas turbines, heavy fuel oil powered plants, coal power plants, geothermal power plants, wind and PV utility scale technology. It has also hydropower plants and a biomass power plant. Once I have defined my reference energy system, I proceed with the optimization. Optimization has a very specific meaning. Optimization means finding the minimum or a maximum of an objective function, of a function, subject to a series of constraints. In most of cases of energy modeling, the objective function is the net present cost. So my goal is to minimize it. So I have to find the minimum net present cost for the system, respecting a series of constraints, such as the energy balance, the power balance, technological constraints, so I cannot produce more energy than the power installed, market constraints, and economical constraints. It means that I have to find the best economical solution, respecting all the natural and physical constraints of my system. Just to give you a quick overview of what it means to optimize in 2 dimensions. This is an example in 2 dimensions. Let's suppose that I have to maximize x plus y. And my first constraint is x greater than 0, y greater than 0, x smaller than 3. So I start drawing my constraints on the plane. Y smaller than 4 and x plus 2, y greater than 2. Suppose that all these small constraint equations that I just gave are the constraints I mentioned before. So I cannot produce more energy than the power installed, or availability of solar resource is only during the day. So these are physical constraints to my model. Whatever falls inside my constraint is called the physical region, meaning that whatever point inside that region satisfies my constraints, but only one of those points is the optimal point. And if I follow the borders of my feasible area, I will eventually get to my optimal solution. That is, in this case, x plus y equals 7. What does it mean? That all of the solutions inside the feasible area satisfy my constraints. For example, if I have a country and I run it only on coal power plant, of course it works. It's something that does not break any constraint, but it will not be the cost optimal solution. So it's a solution, but not the optimal solution. Through this algorithm, following the borders of my feasible region, I will find my optimal solution, whatever way I go around the borders. That was a simple two-dimensional example. In the energy models that we work with, we are working in n dimensions, but the concept is exactly the same. This is a list of different energy models. You can see Markle and Times developed by the IEA. You can see Homer developed by the NRL, the National Renewable Energy Laboratory of the United States. You can see Message that is used by YASA and by RENA. You can see LEAP, very famous. And these are all proprietary software, means that you have to pay for using them, and you cannot see the source code. While we have a set of open energy models, such as the ones that I'm going to give you some examples later, that are were born in the last years on the wave of open energy modeling initiative. Meaning that within this initiative, we aim at building models that are free to use, free to download, but also their source code, so the code in which the model is written, are available to the public. And whoever wants to use them or even change them can change the source code or verify if the source code respects some prerogatives that the researcher has in mind. Okay, so now switching to the particular aspect of off-grid energy system modeling, so sizing microgrids for access to energy. We have a software in-house. It's an open source software that we developed. It's called MicroGrid Spy, and has as an input, as you can see here, also different load curves. We can work with the different load curves. We provide availability of resources, and as an output, I will have as a result the size of the different available technologies that I have, such as PV size, battery size, genset size, to satisfy that particular load. And I will have also as an output the investment cost and the yearly O&M. But it's fundamental to remember that the optimization, the mathematical optimization, is just a step of the energy planning. It's not to confuse energy planning with energy modeling. So we found out, and we strongly believe, that it's fundamental that every time that we carry out also, for example, the sizing of a mini-grid, the first step are made together with the community. So we have a strong stakeholder engagement and data collection on the field to identify the needs, because only by identifying the needs of the community, we can then formulate demand scenarios, because with the electricity, we aim at providing services that will then give the possibility for development to the local community. We also assess locally available resources. With those informations, we proceed to system optimization. We have as an output optimal sizing and optimal dispatch. And with these two information, we can proceed to cost analysis, tariff identification, business model proposal, and then construction of the mini-grid. So the entire approach that we follow is always centered on people, because the sizing of the system is strictly driven by the demand. And the demand is evaluated on the needs of the community, not assigned a priori. Access to electricity is key for fostering the birth of new income generating activities. So we also take into account income generating activities that can foster development. And of course, we always work in line with the most recent literature by the World Bank, for example, and other institutions like that. But it's fundamental to remember this particular aspect. In fact, from this idea that the modeling itself should be just a part of a wider process of energy planning, we developed the comprehensive energy access planning. So as we said, we have this microgrid supply model, okay, that needs load demand and needs renewable sources time series, and provides me optimal capacity and NPC, so net present cost, and SUE, so the costs. But this is just the central phase of a bigger framework that that relies on this concept that mathematical optimization is just one step. And for this reason, we developed this comprehensive energy solution planning framework, in which we proceed by steps by identifying the priorities of the communities we are working with. We then proceed to the diagnosis, so load demand identification and resource assessment. Then we identify the correct technical solution. We then proceed, only then proceed to technical optimization by means of energy system models. Then we provide a set of ancillary activities, and then we evaluate the impact. In detail, what we mean is that in the priority energy needs identification, what we do is understanding what are the services that can be household services or education, healthcare, production services. So whatever energy is needed for in the community. Then we translate that into energy requirement. And on the same side, we estimate resource availability, because it could be easy to incur in the error of saying, okay, I want to make a PV mini-grid because PV now is the cheapest technology, but you didn't realize that there is a river running by the village, and it would have been much easier and much more cost-effective to build a hydro-based mini-grid. So also this is very important. Then, once we understood the local context, the needs and available resources, we identify the most suitable technology. And only then we proceed to the mathematical optimization of the technology. As an output, we will have the sizing and the costs. And with that, we also identify a set of ancillary activities, such as access to the market, access to credit. So activities that are not strictly connected with the mini-grid itself, but without which it would be less probable that the energy allows possibilities for development, because energy itself is not, it's sufficient, it's necessary but not sufficient. So we need also other kind of activities to support the community to embrace energy and start a development mechanism. Then we perform an impact evaluation analysis, and we ask ourselves if I actually met the priorities that I had identified in the first step of my process. But now, to get a bit more practical, I will give you an overview of some studies that we carried out with our models and with our framework. So the first example is the sizing of a mini-grid in rural Bolivia, Latin America, where we combined two softwares that we have developed here at Politecnico. The first software is RAMP. It's a simulation software that, knowing which appliances and when are used by specific categories of users, we can derive stochastically generated load curves for the entire village. Okay, so we can use use of appliances and patterns of use of appliances into load curves. Then are inputted to the energy model. In this particular case, we performed a two-stage stochastic optimization, meaning that we didn't only designed one load curve, but we designed different load curves depending on possible evolutions that could have happened in the village. And with the two-stage stochastic optimization, we were able to find the optimal solution that would have been the best, no matter which scenario was going to happen. The second example is something similar, but we added the concept of load evolution. So not only different load scenarios, but also load evolution. So since energy will be consumed gradually more and more through the years, once the community actually reaches economic development and starts to use energy also for productive uses, and they have the economic possibility to purchase more appliances, we developed the same software, but with the capability of generating increasing demand over the years. And the impact is clear here, how considering a multi-year approach allows me to have a very lower investment cost, because if I know that in the first year I will not have all of the consumption that I will have in the last year, I can consider to delay my investment. So I can install only half of the PV panels, for example, in the first year, and install the second half 10 years later, for example, when it will actually be needed. And the last example is when we modeled a mini-grid, but not only from the electricity point of view. So what we did was exploring the synergy of the electric sector of the mini-grid with the domestic hot water system of the households. So we suppose that we could connect electric resistance inside the tank of solar collectors to keep the water warm. And by allowing the system to exchange energy between the electric side and the thermal side, we were able to achieve, as you can see, more than 50% reduction in the net present cost of the project because of the synergies between the two sectors, from the electric side and from the thermal side. So these were 3 examples of how we used the open source softwares that we have in-house to size different kinds of rural mini-grids and with different approaches. These are some of the literature that I used for designing this presentation, and this is the end of my contribution. If you have any questions, I'm open to answer them now or at the end of the class as well. Okay. Maybe you have to process all the information. I will now leave the floor to my colleague Nicolas, and I'm here also at the end of the lesson. So.
Okay, can you hear me? You should please
Yes.
write in the chat if you can't.
Yeah, we can hear you.
Okay, thank you, Darlene. Let me show my screen, and then we can move to the third layer of our approach, which is the one related to industrial ecology. So tell me when you can see my screen. Okay, you should.
Yes, we can see it.
Thank you again, Darlene. So as I was saying, we are now going to talk about the third layer of the approach that we are using here in SESAM. So the one that is related to optimization, but with a mesoeconomic approach. What does it mean? It means that we are trying to put in an economic context what has been analyzed on a single sector, which is the energy sector. And in this case, we are actually going to bring the relevance of the energy sector and energy consumption in general to the climate issue. So my presentation today, I'm going to talk about the issue of carbon emission reduction, and I will also talk about how industrial ecology can help us in facing this challenge. And in particular, we are going to focus on the environmental input-output analysis, which is one of the many methodologies of industrial ecology, as we are going to see. So feel free to stop me and ask questions if you like, and let's go with the first block of this presentation. So we know that there are many sustainable development goals. The one that is related to climate change is the 13th, that is called climate action. So we see now a lot of interest, at the very least in Europe, for reducing carbon emissions, so in greenhouse gas emissions more in general. But actually also other countries are joining the challenge. We have seen recently Japan, South Korea, but also China and India, maybe with some more decades with respect to European countries or USA, which is also trying to have an agreement with China for addressing the objectives that were in place. So the first point we think is why it's so relevant. So why everybody is trying to reduce CO2 emission. Actually, this topic is very complex. There are many fields of science that are trying to answer to this question. In particular, here I'm reporting a website that is putting together many studies that are attributing extreme weather to climate change. So studies that are trying to understand if a certain extreme weather event can be associated with human activity. This is actually difficult to be done. In this website, you can have access to this interactive map where you can see all these studies. But in general, we can say that the human activity, as the IPCC also recently stated and highlighted, is increasing the relevance, so the intensity and the frequency of these extreme weather events that are not 100% related to the additional amount of CO2 that was released in the last century, but most of them are. So, but let's try to introduce industrial ecology methods, but also at the same time trying to grasp the magnitude of the problem that we are trying to face. So here I'm reporting an estimate that was provided by Professor Lenzen and colleagues in an article that came out late in 2020 that tried to give an assessment of the reduction of greenhouse gas emissions at the global level and also of GDP, so gross domestic product, on a global level. The model that was used was an input-output model, and the estimates of the reduction was around 4.5, as you can see here. And what is really interesting to me, and actually gives you really the magnitude of the issue that here we're trying to face, is that what happened with the COVID-19 pandemic during 2020 leads to a reduction of CO2. That is what we should do if we want to be on track with the dark green pathway. So trying to keep temperature within 1.5 degrees. And this is very, again, a very important reduction. And on the other side, still for the problems that occurred during 2020 related to COVID-19, also the GDP was importantly impacted. The estimates that Lenza and colleague provided, it's similar in the reduction in relative terms to what happened to greenhouse gases, and is around 4.2. But what does it mean? It means that if we want to have a visualization of this reduction, it means more or less to cut out Germany out of the pie of gross domestic product at the global level. So just also to open a parenthesis on the on questioning about the estimates that was provided by this industrial ecology model, we also provide here in this presentation an update. So what really happened? Actually, really, it's not the right word, because this is something that is still assessed, especially for greenhouse gas emissions, which is actually always an estimate, but the contraction was actually more important than expected by the study we just showed. And the GDP was actually a little bit better in terms of reduction, in the sense that the decrease was only 3.5 against around 4 in the what's showed by the study. And here I'm reporting the website that I used to update this value, which is called Carbon Monitor, which is comparing the emission that occurred during 2019 with respect to the 2020. And here you can see this visualization, but I suggest you to have a look at the website yourself. And on the GDP side, there were International Monetary Fund estimates for 2020 that proved, again, the contraction to be smaller than expected, but now we see that many issues are coming together with the pandemic that is still going on. Okay, but let's come back to carbon emission reduction as a challenge. So we see how big is the challenge. We have seen how the reduction of consumption that occurred during 2020 was basically bringing also a reduction of greenhouse gas that is in line with what we need to do every year. But actually, we are not supposed to reduce emission only by changing consumption patterns like what happened during 2020. Our best weapon is actually technological change. So technological change is what we need to reduce carbon emission intensity, which is the way in which the inputs are transformed into outputs with respect to carbon emissions. So what is carbon intensity? We can provide a very simple equation, which is just a division. On the numerator, we have the total amount of emission of a certain jurisdiction. In this case, take your country or my country, and divide this by the total amount of what was produced in the same period, which usually is measured by means of gross domestic product. Okay, here I provided some trends of carbon emission intensity for China, United States, and Italy, for example. As you can see, there are multiple ways of reducing this ratio. In the case of China, we had actually an increase of the denominator that led to this very important reduction of carbon intensity. In the case of Italy, the reduction is still a reduction, even if it's smaller, because the GDP is actually constant in Italy, while we did a small part in terms of reducing CO2. So this ratio is like this. But what I would like to stress with this picture that may look silly is the fact that technological processes are not so spontaneous. So you cannot have a more efficient plane coming out of an older plane. What you need to improve the technology is actually three things that are very interconnected one with each other, which are demand, investments, and policies. that are actually orchestrating this interconnection. I give here an example of what happened thanks to the connection between these three levels. Here you can see the GIF, an animated GIF of the battery pack price according to Bloomberg, which is collecting a lot of data about battery pack price, that actually showed a very important decrease in average terms. This is a weighted average value that, of course, is considering the automotive sector that can buy battery pack at a very high level, very high volume, so smaller price, and also smaller projects, smaller volume of battery packs that may be higher in terms of cost. But overall, the trend is like the one that is provided in the GIF. So more or less a reduction of 90% in 10 years, which is quite impressive. But what happened? What is going to happen also? This is another picture from Bloomberg, which is showing the expected demand of battery. And so we see that many investments are provided, investments are making the cost of the technology smaller and smaller, but the issue is that companies are trying to get a bigger pie of an increasing demand. And the increasing demand is probably pushed by policies, for example, in this sector, related to the need of reducing emission, also in the private transport sector. Okay, so this is the interconnection between these three pillars. Another example of reducing costs is evident in the electricity sector. What happened, for example, in the solar photovoltaic sector? Actually, the technology was super expensive some decades ago, but was still used for producing electricity in the space, because actually it's impossible to have a combustion without air, and you don't have an atmosphere in outer space. So PV was actually a good solution, even if very expensive. But with the objective that now we are facing as a global community, political and financial will brought the technology to other level in terms of cost. As we have seen for the battery pack, this is the levelized cost of electricity by source. So you have on the y-axis the cost per megawatt hour, and on the x-axis the cumulative installed capacity of different technology. We have offshore wind, quite good reduction, and basically we have a learning rate of 10%. What does it mean? It means that every time we have a doubling in the cumulative installed capacity, the cost of the megawatt hour decreased by 10%. This same reasoning can be used for photovoltaic, and this learning rate is actually one of the most, the highest we have seen in technology in general, and brought the cost of this technology really at lower, very, very low levels with respect to just 12 years ago. Okay. At the same time, some other technology were constant or even increase in terms of cost per megawatt hour. And this is something that is happening for technologies that cannot really scale anymore, because we already know how to optimize it at the best way. Okay. So we have seen that there are policies that can influence demand, which can influence investment, that can bring the cost of technology at the lower levels. But now it's time to try to understand how this can be grasped within the industrial ecology framework. So what is industrial ecology? Industrial ecology is the science that studies socioeconomic metabolism. So basically, we have from one side the social sphere of causation, which is the one where we as human beings are fulfilling needs by buying commodities, products that we can find in the markets. Why? Because somebody, usually industries, brought those commodities in the market. But in order to produce those commodities, they are extracting resourcing from another sphere, the biophysical sphere of causation, where also some emissions are released. The industrial ecology is usually focused on the frontier between the boundary of nature and the anthroposphere. And in the case of CO2 emission, actually the connection between this ton of CO2 that we release today with some feedback loops that will determine the some level of damages that will come somewhere in our planet at some point in time is basically proving that this concept is right and that we should use this approach to study carbon emission reduction mechanism. And actually, this is also what in general economists think about dealing with emission reduction. So put a price on the ton of CO2 and you will internalize the cost of future damages somehow. But actually, okay, probably is easy to understand, and actually we may agree, I think, on putting a price on carbon because we know there is bad relation with future damages, but way more difficult is to understand what is the fair price of carbon. What do I mean? Usually economists and researchers in general talk about social cost of carbon. So basically, what is the cost for the society of emitting 1 ton of CO2 that you can see here in this picture, as big as a very small house, apartment, more or less. And me, as Italian, I'm responsible for 6 of these every year on average, okay? But, okay, so we know the denominators, the ton of CO2, but the numerator, so the damages, the social cost for all the society is actually depending on many layers of information. So the first one is actually how much are we going to grow in terms of economic development, and also how many tons of CO2 we are going to release in this process. So the representative concentration pathways is a way to think about scenarios in terms of concentration of CO2 in the atmosphere. And also what is the assumption behind the damage that are going to happen for every ton of CO2, very important, of course. But not only that, also consider the discount. So the fact that what we are emitting today will cause damage in the future. And it depends on how much do we care about what is going to happen in the next year, 3 years, or 10 years. So the assumption around the discount rate is important as well. And also the country is can have very different perspective. Think about the coldest place you can think in which you have human beings, and ask yourself if having 1 additional degree can be good or bad for them. Probably if you think very utilitaristic way, with a very narrow vision, you may think that for some countries, 1 additional degree can be good. And many other things. You can play with this assumption if you look for the link in this slide or this paper on the web, in which the results were visualized in a very nice and interactive way. So you can play with assumption and you can find the social cost of carbon by country. Every circle here is a country. You see that some of them are actually negative, the one in green. And if you sum out for all the contribution, the regional contribution, you will end up with a certain value, which is the global social cost of carbon. So, but is this the first time somebody's talking about pricing carbon? Not really, because actually some countries already did something in terms of carbon pricing initiatives. Here I'm reporting this map that is taken from the World Bank dashboard on carbon pricing. And you can see there are two main ways of pricing carbon. First one is having a carbon tax, so a direct tax on the single ton of CO2, which is imposed by jurisdiction, and the target is the emission itself. So we put the price on the ton, and so we know the activity that requires the emission of some ton of CO2, and so we can have the price. Ideally, this should go towards the social cost of carbon if we have a perfect world, okay? But we know and we see how difficult it is to determine the social cost of carbon, how uncertain it is. Sweden was the first country to put a price on carbon, it's now around 110, and this is the highest in the world. But recently, also the price of 1 ton of CO2 in Europe increased importantly. But what is an ETS? An ETS is an emission trading scheme, and is functioning starting from this principle. Okay, we as a nation, as a jurisdiction, we have a maximum carbon budget. So a total amount of CO2 that we decide we will emit in a certain year. So I can take this total amount of emission and sell permits for emitting 1 ton of CO2 that can be sold among agents that are in this jurisdiction. And this is bringing emission targets at a lower level, because if you decide that you want to reduce this total amount, you can do it targeting emission volume. Ideally, if the market has a perfect information, this should bring the cost of the CO2 to the fairest price. That's the idea. But we know that actually perfect information is not actually a true statement in the real world, because many things are unknown. For example, the future damages. As I was saying, the price of 1 ton of CO2 now is around 80. There is a lot of volatility in the market recently, but that was good with respect to what happened in the past, and also with respect the ETS of China that is now very still very low in terms of cost price per ton of CO2, but they just started 1 year ago. Okay, and also Europe also had very low prices for a lot of time, as you can see from this chart that is reporting the price in time, decades below 20 euro per ton. And what do you think about what happened in this period? Actually, as you can see from this chart, the reduction was not so important. This chart is showing to you the production of electricity by source in 4 different European countries, and on the with the black line, the European Environmental Agency here represented the total verified emissions. But do you notice something? I noticed something. I noticed that in UK there was a steeper reduction starting from 2013, but as you can see, the price of the ETS was still quite low. But what happened is that UK was the only country about these 4 that introduced a so-called carbon floor. So a minimum level of CO2 price that basically is setting, again, a floor in this market. So minimum price. This minimum price was around 20. So actually higher than the price of the market of the ETS, and was probably contributing in making the reduction possible, because investors actually knew from 2013 on that the price of CO2 will be at least 19. Okay, so putting this in their plan, they will probably try to reduce the CO2. Okay, That's the principle. Also, another actually limit that can be related to the European ETS, but in general in carbon pricing initiative, I would say, is that we consider CO2 emission and the consequence on climate change as a local problem, but actually the problem is global. And a lot of CO2 is actually traded in emission. What does it mean? In this very complex and colorful chart, you see the flow of CO2 emission, basically the CO2 that is embedded in the goods and services that are exchanged at the international level. You see a lot of stuff, so a lot of CO2 that is flowing from China to US or from China to Europe. This is actually the emission that were released for producing something that was imported by USA and Canada or by Europe. This amount is actually 20%, so not really negligible. And in fact, you can see right now in Europe, at the community level, we are trying to introduce the so-called carbon border adjustments to also considering the emission embedded in these traded goods. And this was anticipated by the agenda of Ursula von der Leyen before she became president. Okay, so again, now we have the context, but we should talk a little bit about the tools that are offered by industrial ecology, which is basically trying to find some innovative solution to complicated environmental problem like the one that we are talking about. So we should start from a characteristic that should be of every industrial ecology tool, which is the characteristic of being multi-sectoral. So being able of considering every agent in a disaggregated way. And we can divide these tools between contributional approaches and attributional approaches in terms of life cycle assessment. What does it mean? Attributional approaches are just assigning responsibilities for impact to different agents. Consequential approaches are trying to do something more, a little step forward. So basically also trying to give an assessment of the effects of attributing those impacts to those different agents. Here are reported the 6 main approaches of industrial ecology. As I was saying, this first characteristic is well distributed. But for example, time evolution is not as well. And only some of these approaches consider time explicitly. Also, not all of these tools can consider different agents' behavior. This is something that you can see in economic equilibrium models or system dynamics and agent-based models. Some other models are ruled by the principle of comparative advantage, which is quite important in technology choice models. And finally, the technological infrastructure detail is important. So we see that all of these tools are multi-sectoral, but the granularity of the sector is important. So some of these, usually the attributional one, are very detailed, but also recently input-output models are becoming more and more detailed because a lot of effort are in place to represent the accountability of nations or group of nations. And that's why we're going to focus on these models, because we think that this approach is growing and becoming more and more interesting. And that's why now we're talking about environmental input-output analysis. So some historical hints before starting. Input-output is actually a methodology that is coming from economics. This guy is Vassily Leontiev. He won the Leontiev Prize. Sorry, not the Leontiev Prize, the Nobel Prize for Economics. Now there is also the Leontiev Prize by his name. And he had a very, how to say, global experience in terms of education and also of working, and he studied in Berlin in England, and then he moved from he worked in Russia, and then he moved to USA. And while he was in USA, he was asked with this question: how much increase in mineral production, in labor demand and final consumption is implied by a 10% increase in steel production that may be needed for the war? That was the issue at the time. And maybe the answer to this question can be trivial, because you can think, okay, I need to make a tank, so I need this amount of steel. But in this process, you are neglecting what you need before having the steel. And he came out with the first input-output table, and that was used for answering the question. He won the Nobel Prize for Economics in 1973. And today, actually, GDPs, we saw GDP at the beginning of the presentation, gross domestic products, are computed from input-output tables with a top-down approach. Well, actually, GDP is computed in many ways. This is the relation with input-output. But of course, behind this model and methodology, there are assumptions, like in every model. And in particular, in input-output model, assumption should be very properly handled, because the underlying principle is that economics and the interconnection between sector is behaving consistently. What do I mean? I mean that material balance is implied, and at the same time, a financial balance is implied. So what is provided as an output should match with total cost of all the other agents of the table. And also, if you need one pen, you need to produce and consume some intermediate inputs. If you need 2 pens, you just need to produce and consume twice as much as what you needed for 1 pen. This makes sense for 1 to 2, probably. But if you take this from 1 to 1 million pens, you can understand that will be some scale effect that will change slightly the structure of my economy. Input-output is not considering this. Okay, so this should be as a limitation to always remember when you see results in this case. And also pricing variance is coming with this assumption. And this is just, filling the table at the end of the day and using the table. But there are also other assumptions that will be needed if you use input-output as a model. So this is a table, an input-output table. And as you can see, this is actually a multi-regional table. So a representation of the economic flows that came during one period of time, usually 1 year, and can be disaggregated in multiple regions. And then you will have a multi-regional input-output table, like the one that I represented here as a sketch. You see your country, you see my country, and a rest of the world region that is basically taking all the other countries in one unique region. And what can you find on an input-output table? For sure, you can find information on the technology in the sense of kind of a receipt to produce 1 pen, as I was talking, okay? And this information can be related to region by region. So maybe the request of ink, of Italian ink, by an Italian producer of pens, but so you can see the interlinkages between industries in the same nations. But on the other side, you may have some inputs from Rwanda to produce something in Italy. Okay, this can always be true. The same can be said also for final demand, which is in the orange side. And with the same principle, we can distinguish between final consumption of domestic goods and services and of final consumption of exported goods and services, okay, with the same idea. A very important layer of input-output tables is actually value added, or also called factor inputs, is where you find information on the use of capital, labor, taxes, and subsidies that were requested alongside with the production of a certain sector, okay? And since this is the environmental input-output table, you also find some environmental layers where you can find, I don't know, information on water use, on energy use, or on the release of emission, like CO2 emission. So in general, inflows or outflows of environmental activities. Okay, so if you see the information and you study the table at the column level, you will find in this example the total inputs required to a certain Rwanda sector for producing its annual output. And on the row of the same sector, you will find where the output of this same Rwanda sector came in this 1 year. In a very sketched way, we can now see the advantages of input-output, but also what you need as an input to the model in order to have some results. So let's start with the easy question, which is, how can we allocate CO2 emission responsibility to different regions? Okay, we know that we have to reduce emission, but we have a lot of regions, nations in the world. So if you want to have an answer to this question, you will need to give to this methodology as an input information on the geographical and sectoral detail of your table. What are the impacts? So in our case, CO2 emission, and information on the technology. So basically the table that we just see. And as an output, you will find the environmental, social, and economic impacts. So what's the answer to the question? Here you see an answer to the question where territorial and consumption approaches were still possible to answer to the same question. Because if you use a territorial or production-based accounting, you will give to every country the responsibility for just the emissions that were released within their boundaries. But it's still possible, and you can see the dotted line, dashed line, to have a consumption-based accounting in which all the jurisdictions are responsible for the emission released all over the world to produce what that jurisdiction consumes. And you will see that China has more or less gigaton, and Europe from the other side has more emission at the consumption-based accounting level. And why this is important? Because with the production-based accounting, something called carbon leakage can occur. What is carbon leakage? Is the phenomenon that is occurring when you put a tax on CO2, for example, in Europe, and as an effect of this, some industries will be moving away. So maybe you will increase, as Europe, a import from another country that is in general more carbon intensive, maybe. And as a result, you have a tax on your country, but at the global level, the emission increased. And just to stress this principle, here reported one of our contribution for the IEA, and where this concept is stressed. And you see the producer responsibility as a sum of goods for domestic consumption and also the exported goods. While if you have a consumer responsibility approach, so CBA, you have the goods for domestic consumption and the import goods, and you are not considering exported goods because it's consumed somewhere else. So in general, we see that reducing pollution, or in this case, CO2 emission locally, doesn't mean global improvement. And one should always have an analysis of the supply chain in order to consider also indirect effects. That's what we try to do with the case study that I'm now presenting to you to conclude my contribution. Here we ask ourselves, what would happen if tomorrow morning we get up and we have the same emission trading system that I also talked about today to you, with a shift in the approach from a production-based accounting to a consumption-based, so also considering emission taking place outside of Europe. Since, as my colleague Nicolò Stevanato told to you, we don't have another planet to make an experimental approach, because it would take a lot of time and resource, so it's not possible. We should have a model of the world. And this model of the world will be always a simplification of reality. And in this case, we're using a multi-regional input-output approach together with a linear optimization. And this is, at the end of the day, the world trade model that you can find in the literature. And this approach is, again, taking place as a comparative statics. So asking yourself, what would happen tomorrow morning? In this case, there is no time to improve the technology. The only thing that we can do, so the only degree of freedom on the model, is change the production and trade patterns of the society. And the principle of comparative advantage that I cited before is taking the lead here. So basically, the production of goods and services is fulfilled by those countries that can produce at the lowest cost. But of course, since resources are limited, at a certain point, somebody else will start producing at the additional higher cost, and then you will have your solution. So what we did was basically taking an input-output table, multi-regional, global one, and writing some equation, having a case zero that is a good representation of reality, and then we are perturbating this representation of reality, imposing stricter and stricter carbon emission reduction policies, one for PBA, one for CBA. So these are the equations of the model. So we need to minimize global costs while satisfying the demand at all the levels of sector and regions, while not exceeding resources. And of course, we cannot have negative production. This is more a mathematical constraint to make these things reasonable. And this is the result of our study. So on the right-hand side, you see the consumption-based accounting. On the left-hand side, you see the production-based accounting. And in both of these graphs, we have the same Y and X axis. On the Y axis, you have the CO2 variation that is expressed in relative terms with respect to baseline level of CO2 emission. And on the X axis, you have the reduction of the carbon budget that in the first case, in this case, is accounted with the PBA principle. And on this case is accounted with the CBA principle. So the more you reduce the carbon budget, the more, of course, in the first case, the Europe is reducing its CO2 emission. This is actually what you're asking. But as you can see, as an effect of reducing emission in Europe, we have a higher reliance on rest of the world emission, it's rest of the world production that will come with additional emission in the rest of the world. And as a net effect that you can see on the black line, you have a global increase in CO2 emission while having a reduction in Europe. But what you care at the end of the day is the global emissions. And this is not coming with the CBA approach. So we see that for Europe, CBA policy is not making carbon leakage happen, at least from the modeling approach that we use. So this is actually bringing support to what Europe is trying to do today with the border trade adjustments. Here you find detailed results that you can find also on the paper that you can see in the bottom of the slide. And here you will see also the effect on the GDP and by sector or region. And that was all from my side. I thank you for your attention and I'm available for your questions, if there are any.
Okay, thank you very much, Nicolò, and to Nicolò and Francesco too. Okay, so thank you also from Ismail in the chat. I don't know if we have questions for our partners from Politecnico di Milano. Again, as usual, feel free to use the Q&A box, the chat, or raise your hand. I know these were quite really 3 different aspects, a bit maybe complicated, so maybe you need to digest it a bit. As you know, ASAP, probably by the end of today, you will have available on also on YouTube today's recording so that you can rewatch it, and maybe some new questions will come up. So in this case, feel free to write me so that I can forward it to our partners. Also, you have their emails at the end of the presentation, so feel free to do it. I don't see actually any question. So what time is it? Okay. So I will leave you a few minutes to write in the Q&A box. As I said, if you have questions. In the meantime, just to remind you, tomorrow we have a lecture on SDG 7.1. So on access to clean to energy, so to clean cooking and electricity. Then next week we will have the 2 final lectures, so that we have solid biofuels modeling and the final wrap up and quiz, in which you will have the opportunity to give us feedback on the overall program, etc. So as I said, I don't see actually any question raised hand. So if there is no comments from our partners from Politecnico di Milano, I would thank them. Thank you guys, Nicolò, and Francesco, for being with us today. And see you next time, probably with Uganda, which will be our 10th country, probably at the end of May or beginning of June, but we will keep you posted. Thank you very much. Have a nice day and see you soon.
Thank you.
Bye, everybody.
Bye.